Let me invite for the next talk Professor Enrique Kajomovitz. That's how one pronounces the J.
No idea.
And who is a member of the young generation of leaders of the experimental high energy physics in Israel. He's from the Technion, and he will tell us about LHC and beyond. Please.
Okay. Thank you very much. Okay, so normally I choose to talk about beyond standard model physics, but today I wrote the talk mostly about what we learned about the standard model at the LHC. And Yuval is the same age as the Technion. So also the Technion was 15 when they invited Yuval to come. And I'm going to talk about the Higgs bar mitzvah, which is nice. Okay. Okay, so this is, Shikma showed this, but first I want to light your imagination. What the LHC means. And if we look at this graph, so the line in the top is a total proton-proton cross-section. And the things that we're interested are, let's say, 10 orders of magnitude below. And if you okay. So if you think about it, the LHC, let's say, we have built the best. We're in space. We build a ball shooting machine, the best that we can. Every second, every time we throw balls at Earth, we throw 10 to the 11 balls, and we manage to hit Earth every time with 60 balls. So that's how difficult it is to do these experiments. And if we think about what it means to hit this thing, is what we want one of these balls that we are shooting at Earth to hit the size of a basketball court. So it's to learn about this process, we need to shoot a lot of balls. And so the LHC is this kind of machine that is able to do that. It's a huge achievement. I think that people dreamt, they had a dream to build this machine, and they built it. So at the LHC, we have bunches of protons circulating, roughly 2.5K bunches of protons, and every bunch has about 10 to 11 protons. And every 25 nanoseconds or 40 million times per second, these bunches meet each other at one of the experiments of the LHC and produce some random process that its probability is described by the standard model. And the experiments at the LHC face this huge challenge about how to collect the data coming from these collisions. If we would take the rate of data, just raw data coming from the LHC collisions without doing any trigger, we would have 40 million petabytes of data per year. So it's a huge amount of data, and we need to make it somewhat manageable. So there's a huge trigger system that takes this data into manageable chunks and enable us to understand nature. Today, the LHC is running, well, today the LHC is not running, but yesterday it was running with about 60 interactions per bunch crossing. And we were able to handle this amount of data per bunch crossing. So this is the standard model. It's a fuzzy picture. I didn't mean to make it a fuzzy picture. But the LHC, I think, had the major achievement of discovering a new kind of force. The Higgs particle is a completely different animal from everything we've seen before. It's a scalar particle. I think the charges are not quantized in a way. It's a scalar field that is everywhere, and its vacuum expectation value is non-zero. And in only 13 years, we have learned a lot about this new particle. So in 2012, as I said, the bar mitzvah of this particle, the two main experiments at the LHC, or two general purpose experiments at the LHC, simultaneously make this announcement of seeing sufficient evidence of the Higgs particle. And I remember as a student, I was finishing my studies, but I remember seeing in these slides by Fabiola, which have these crazy fonts and colors, but they surely make you remember what she says. This thing, this is just the beginning, and we are going to measure everything about this particle. And I thought it was so far. You know, I didn't understand that within this period of years, we will be able to measure so many things about this new thing. And the first thing is to measure the mass of the particle. And you can see that today we understand roughly, the two experiments understand the mass of the Higgs to roughly 1%. The experiments at the beginning combined their results, but today each experiment has a better result on its own right now. So we have been able to measure the width of the particle. So, you know, in little more lay person terms, measuring the width it means measuring how many decay modes this particle can have. And since we're able to measure the decayed modes or predict what should be the width from the standard model, if we measure something different, it really will be an indication of physics beyond the standard model. And the way this is done is, since the detectors don't have sufficient resolution to measure this 4 MeV order of magnitude of the Higgs width, we measure the relationship between the off-shell and on-shell production. And we're able to determine the Higgs width to be as predicted by the standard model. Another interesting property of the Higgs, and I think the first thing I thought when the results were presented is, how will we understand that this is really a scalar particle? It's just not just another bump. And so it is possible to study to do an angular analysis of the decay products and understand and compare whether the distribution of the decay products matches the hypothesis of being scalar or another spin parity state. And so many alternatives were tested, and today we know that, you know, we rejected the other alternatives to more than 99.9 confidence level. How about what the Higgs explains to us about how the different particles interact with it? So what you see in this x-axis is all the different modes of production, and these are different decay modes. And you can see that the measurement of the different decayed modes and production modes fits our understanding of what the standard model should be doing. This is another way of understanding, of seeing the relation between the Higgs measurements of couplings and the different masses, and this works amazingly well. So the Higgs works well. How about the properties of electroweak forces? So in this case, we can test lepton flavor universality, and it agrees extremely well with the standard model. We can measure the W mass. So the W mass gets these corrections, and if we would find the W mass here, as these guys did, so we would know that something is missing from our understanding of how things work. But it turns out that when we measure it at the LHC, this fits the standard model very well. We can also measure the production of multi-boson states, and you can see this is kind of crazy processes where you have forces interacting with each other. So you have W talking to photons, or W is talking to, you see, the World Wide Web. Everything is there. And so all of these things predicted by the standard model are measured at the LHC, and everything agrees very well. It's really beautiful. But
so are there experiments to challenge standard model, or just incorporate?
I think I'll talk about it. So we can measure the mass of the top, and we can measure what happens when the top is produced, and we can try to understand if, when we are producing pairs of tops, somehow they produce entanglement. And we can also analyze the angular properties of their decayed products at different energies. And when this analysis was being done, they observed some excess over the prediction. And it turns out that the explanation for this is that a new bound state of TT bar is being produced. So this is a thing that we didn't think it was possible to measure within the standard model, that the top would decay too soon to be able to measure this bound state. So it's very, very interesting how we went around from measuring quantum mechanics property of entanglement to having an understanding of some basic production of a bound state. Well, not talk about the LHC would be complete without the incompleteness of the standard model. So the experiments, we have tried to think about all the possible generic ways in which a theory that would extend the standard model would manifest itself, and give us some sort of observable that we can look for it, and then if we find it, it's great, and if we don't find it, inform us about how we should constrain our understanding of what beyond the standard model physics should look like. And so the picture that we have is that most of the ideas that we had about what physics beyond the standard model would look like if it has an energy scale about a TeV, they seem to be very disfavored by the LHC or excluded, unless it's a kind of a theory that we haven't thought about it. And other things that we have thought about is what if these new theories produce long-lived particles, that they are difficult to detect without making a dedicated experiment. So the LHC experiments are also target those. Just to give an example of thinking really out of the box, there is this phaser experiment that was, I don't know, some kind of lucky accident. So the thought was whether it was possible to take advantage of the huge number of QCD states produced in the direction of the beam, that if these QCD states would couple somehow to new physics and then decay to it, and this new physics would be long-lived and travel towards a detector that is far away, we would be able to see it. And it turns out that the LHC somehow has this cavern that we can put the detector directly with the line of sight to the Atlas interaction point. And this detector can be designed a rather simple detector with a few components, and we would be able to be sensitive to a long-lived particle that is produced at the collision, travels through the rock, arrives at the detector, then it decays, and we can detect its decay products. And this experiment, comparison with the other huge LHC experiments, was built in 2 years, mostly with donations from other experiments and a donation from the Simons Foundation, and already is giving us some new understanding of where new physics is not. So many questions remain, but I think that I've thought about this in different ways at different points, but the Higgs is really a new thing, and we can think about this as a new laboratory. It's a completely new type of force. It's giving answers to some questions that we weren't sure that this was the mechanism for spontaneous symmetry breaking and how particles get their mass. As Michael was saying, now we want to understand the Higgs potential, and this requires from us to understand the Higgs self-couplings. So the LHC still has some chance to give it a shot to measure the Higgs couplings, but this is very difficult at the LHC. And we know that the standard model is not a complete theory of nature, but so far we don't have any hints. So maybe the Higgs is the portal to new physics, and building a E plus E minus collider that in the future could be upgraded to a PP collider may be the way to go. So what is being proposed at CERN is to build this FCCE, and in their program they have continuation to this 2065, but I'm not planning to be in that experiment. But this is an incredible machine. It's I think I read in one of these reports that in 3 minutes of operation of this experiment, it would produce all the data of LEP, something like that. It's like crazy machine. And if this machine is built, we should be able to measure the Higgs self-coupling and understand this. And I think more amazing, well, I don't know if more amazing, but we should be able to even measure the electron Yukawa, which is, first generation coupling to the Higgs. Electrons are everywhere, and we don't know if the Higgs is giving their mass. So it's a big deal, I think, or a small deal. But okay, so I just want to summarize. The LHC has been an era of discovery. I think a lot of us, because are very interested in physics beyond the standard model, often forget how incredible is this machine, and how incredible it's that we discovered this completely new animal, and it's opened a completely new ways of looking for different physics. Unfortunately, no hints beyond the standard model at the TeV scale, and this tells that we should think harder about new physics. And we should think about new collider, as Shikma was saying before. That it takes a very, very long time to build these machines, and we have to start working on that, because if not, then we'll have a generational gap. Will not allow us to do these science. Okay, thank you.
Thanks to Enrique for this very comprehensive and interesting discussion about the Higgs. And yeah, we have time, please. And the microphone. No, it's broadcast. It's also broadcast, so we need the microphone.
I think the main problem of the standard model on top of the masses of the neutrinos is why is the Higgs mass protected? It is a scalar particle and can acquire all kinds of radiative correction up to the highest scale. And all the theories that suggested explanation require new particle and new interaction and all that, and nothing had been found up to this day.
This is a sad 1 TeV scale slide. I agree, but I think the LHC so far is not telling us where it is. You can, maybe it's 10 TeV and not 1 TeV, but yeah, we don't know where.
This is something to be kept in mind.